Okay, in this video we are going to study about continuity on an interval. On an interval, the continuity related with the domain. Function is continuous at all x is element of A, then continuous in the domain of A. So if you remember the domain of the question function, you can already find the continuity in that interval, in which interval it is continuous. Okay, if you remember, for the polynomial function, the domain it was R. What about the continuity? Continuity. So it is same. It should be. What about rational numbers? Fx is equal to, if you remember the function form, it was equal to fx over gx. Fx over gx, let's say, fx over gx. So gx must be different than 0. This was. So the continuity gx is not equal to 0. For when gx is equal to 0, function is not continuous, discontinuous. When gx is equal to is not equal to 0, function is continuous. When gx is equal to 0, function is discontinuous. It's going to be. Okay, as you see, I'm writing the same thing. That's why I'm not going to continue to write under the continuity part. So for the radical functions, if you remember, we were writing like this: fx and root of fx. And here the form is ax. If n is odd, function is defined for all real numbers. If n is even, fx must be greater than 0. Fx must be greater or equal to 0, greater or equal to 0. For the exponential function, if you remember, the form was a to the power of fx. The domain was all real numbers. And for the logarithmic function, logarithm base a fx was the form, and it is like radical expression. Fx must be greater than 0 was the domain. Fx must be greater than 0. This was the domain of the function. So we can easily say here, for the continuity of logarithmic function, fx must be greater than 0. How it is here also, and this one is going to be for the continuity R, and this should be fx is greater or equal to 0. What is the domain? The continuity is same in the interval. Okay, now find the largest interval. This function is rational function. This function is rational function. So for the continuity, I need to find the domain of it. Or we can write like this: x squared minus 5x plus 6 is not equal to 0. You know how to factorize this one. Minus 6, the sum is going to be minus 5. The product, it should be 6 plus 6. So I'm going to choose minus 3 and minus 2. Minus 3 times minus 2, 6. Minus 3 minus 2 plus minus 2 is equal to minus 5. When you cross the multiply, you're going to understand this is equal to minus 3x and this is minus 2x, as you see here, and the sum is going to be equal to minus 5x. That's why it is the midterm and it's true. So x squared minus 5x plus 6 is equal to x minus 3 times x minus 2 is going to be. So this is not equal to 0, and x is not equal to 3, and x is not equal to, and x is not equal to 2 is our solution. So domain and function is continuous. Function is continuous at real numbers different than 3 and 2, or 2 and 3 also. It can be 2 and 3 is better. Okay. What about this one? This question is radical expression. For the radical expression with even integer, here even index, the function must be greater or equal to 0. So x squared minus 2x minus 3 must be greater or equal to 0. We have the solution video for the quadratic inequality. You may check that one. First I'm going to find the roots of it. X minus 3 and plus 1 it's going to be, because minus 3 plus 1 is equal to minus 2. Okay, then x minus 3 times x plus 1 is equal to, greater or equal to 0 it's going to be. The critical points x1 is equal to 3 and x2 is equal to minus 1. And when I put these points on the real number line, if this is minus infinity and this side is plus infinity, minus 1 it should be here, and 3 which is greater than minus 1 it should be on the right side. Then the signs, both of the signs are plus and plus. I have to start with plus and minus and plus here. Then we are looking for greater than 0. This interval is greater or equal to 0. This is less than 0, and this interval is greater or equal to 0. So I have to shade these pluses. So these intervals, they are the solutions for us. And with respect to that one, fx is continuous at minus infinity minus 1 union 3 to infinity. Infinity sides always open. Function is greater or equal to 0. That's why greater or equal to 0 sign means you should close the parentheses for the known values. Okay, we have here types of discontinuity. There are 3 types of discontinuity. One of them is removable discontinuity, jump discontinuity. We have seen this one at the beginning of the discontinuity. It is not continuous in these 2 cases I said. And this is the third one, and this is the new one for us. This is infinite discontinuity. And the new thing is the name of the discontinuity here. So here there are 3 types of discontinuity: removable, jump, and infinite one. What does removable mean? If the limit value and the function value, they are not equal to each other, we should make hole here, and we should put the value of the fx function here. Actually here, as you see, fx0 is equal to a, and this part is important. Fx0 is equal to a value. That's why at x0 the limit exists, but the function value is not equal to each other. So this is removable discontinuity. What about jump discontinuity? Jump discontinuity, as you see, the graph is separated, 2 separated graphs we have here, and it's very easy to understand here. When you draw the graph, you should shift your hand for the jump discontinuity. As you see, we understood that part also. And the infinite discontinuity, normally function, if there is no x0, maybe it will be together, but when there is x0 and this is asymptote, you know, this function goes to infinity up here, also here it goes to infinity to this side, it goes to infinity to this side, also it goes to plus infinity as a function value. So we are going to say infinite discontinuity for this case. And the exercise for this one, and this is the last lesson or last exercise was for this topic. Here we are going to have the continuity for each values. For minus 3 at x is equal to minus 3, at x is equal to minus 2, at x is equal to minus 1, at x is equal to 0, at x is equal to 1, and at x is equal to 2, and at x is equal to 3, here 3 value, it should be approximately here. At x is equal to 3, it must be here. Now function is, as you see, when at x is equal to minus 3, function is continuous. Function is continuous. Here function is continuous because when I'm passing through minus 3 for the x value, I didn't shift my hand. Okay. For the minus 2, you see, I shift my hand. I'm starting to this point, then I'm jumping, and I'm starting from another point and continue to draw. So this is also not continuous case. Function is, this one I'm going to write directly discontinuous and discontinuous. And the type of the discontinuity, what is the type of the discontinuity? Removable discontinuity. The third point is minus 1. At minus 1, function again discontinuous, but this time the reason is jumped discontinuity. Jumped discontinuity it's going to be. And at x is equal to 0, when I move my hand from left to right, when I pass it through the 0 at x is equal to 0, I'm talking of course about. As you see, I didn't shift my hand. Function is continuous here. At x is equal to 1, we have discontinuity. And this is removable discontinuity. Discontinuity it's going to be at x is equal to 2, function is continuous. And at x is equal to 3, function is continuous again. Because we don't have jump or removable discontinuity.